last time, one of the things we did were we proved two mean value inequalities. So we proved two mean value inequalities. And let me recall those. And the first one was that, so if you had a function f on some interval from a to b into R, and this function f is differentiable, then it said that there exists some x0 with x0 strictly between a and b, so that the derivative at x0 is equal to the average of the function, or the average of the function at the endpoint. So this is the average on the endpoint divided, so it's average over the length of the interval. So this is what the mean value theorem said. And then there was a second mean value theorem, and that was the Cauchy mean value theorem. So the Cauchy mean value theorem. And that was where you had two functions, f and g, on this interval into R, and they are both assumed to be differentiable. And then again, it was that there exists some x0 strictly between a and b. And if you take the derivative at x0 of f times the value, the difference in value of g at the endpoints, then this is equal to the derivative of g at x0 times the difference in value of f at the endpoints. Right, so that was the Cauchy mean value theorem. So it's a little bit more complicated than the actual mean value theorem, because you had two functions at the same time, and the point here was that you can arrange this x0 to work for both points, for both functions. Right? Let me just make an observation that if if we're looking at so the Cauchy mean value theorem seems like a more elaborate version of the mean value theorem, and it really is, because if you suppose that g here was the function that is equal to x, so g of x is equal to x, I have f here on the interval from a to b. This is again differentiable. Well, if the other function was just this sort of rather trivial function g, of course g is also differentiable, and we even know that the derivative of g at all points is 1, right? So if you are now applying the Cauchy mean value theorem, then it says that by the Cauchy mean value theorem, right, there exists some x0 with x0 strictly between a and b. And so that the derivative of f, so that's whatever that is, that's the derivative of f at x0. The value of g at these two endpoints, where g is just a function x, so this is just b minus a. And the derivative of g is 1. And then it's the difference in value of f at the endpoint. right? And so now if you just divide by b minus a, so this of course implies that f prime of x0 is equal to f of b minus f of a divided by b minus a. So in other words, and so you see this here gives you the more standard mean value inequalities. So in other words, the Cauchy mean value theorem is more general than this mean value inequality, right? Because you recover this if you just let one of the two functions be just a trivial function x. Right? Okay, so that was just an observation. The second thing I want to talk about is something we didn't get to last time, and this is these L'Hopital's rule. And I'm just going to state one version of it. There are two versions, and they're both in the notes, but I will just state one of them. And so this is, so the situation here is that you have two functions, f and g, and they are defined on some interval, say from a to b into r. The interval does not include the endpoint, okay? So these are differentiable. And then we assume that the limit here, we assume that g, of x is, and not only g of x, but also g prime of x are not equal to 0 for all x. And then we assume that the limit here of g of x as x goes to a, that this here is 0, and the same holds for the function f. So this here. And then what you're interested in is that you're interested in looking at f of x divided by g of x, right? So this here makes sense. G doesn't vanish, so this here makes sense. And you are interested in looking at this fraction here as x goes to a, right? If x goes to a, then the denominator goes to 0, and the numerator also goes to 0, right? And the question is, does it have a limit or not, right? And so there's one more assumption here that you need, and that is that that if you're looking at the, so assume also that the limit here as x goes to a of f prime of x divided by g prime. Assume that this here exists and is equal to some L. Okay. And then the claim is that then, so the claim here is that this fraction here, f of x divided by g of x, that this does have a limit as x goes to a, and that limit is actually L. So this is one version of this rule, okay? And there's another one very similar. Okay. And so we want to prove this. So we are looking at, so we want to apply the Cauchy mean value theorem to prove this theorem. And so we're looking at an interval here. So you're looking at say, y. So here you have a, here you have x, and then here you have y, and here you have b. Right? And I'm now going to apply. So we will apply the Cauchy mean value in. But we are applying it on this interval here. Between, so y here is less than x, but it's strictly bigger than a. And this is x is strictly less than x, right? So the function was differentiable on this open interval, so of course it's differentiable, or both functions are differentiable on this closed interval. So we can apply it, and so we get that f prime at some intermediate point, x0, times g of x minus g of y. This is equal to g prime. Again, x0 here is some intermediate point. It lies between these two. G prime at x0 times f of x minus g of y, sorry. Like that. Right? This is just applying the Cauchy mean value theorem. Sorry? What did you say? Oh, yeah, sorry about that. Thanks. Yep, thank you. Right, and so now I just divide. Of course, this here is supposed to be non-zero, so I can just divide. So we have that that f prime of x0 divided by g prime of x0, and then I want to divide by this, but I just need to make sure that this here is that I can divide by it, right? That it's not zero, this thing here. So I have this. Now, think about x as being fixed and do this for all y, right? If I do this for y, where y is very, very close to a, this here becomes really, really close to zero, right? This here is fixed and it's not equal to zero, right? So this here is very close to zero, this is not equal to zero. So this here, if y is really close, if x is fixed, y is really close to a, this is definitely not zero, right? So I can divide by it, right? So for x fixed and y sufficiently close to zero, then you have then g of x minus g of y is not equal to zero, right? And so I get that f prime at this intermediate point divided by g prime at the same intermediate point is equal to f of x minus f of y divided by g of x minus g of y. And now you see that as y here goes to zero, right? So x is fixed still. As y goes to, sorry, not to zero, but to a, this here goes to zero by assumption. This here goes to zero. So the whole thing goes to f of x divided by g of x right? Now the thing is that if you, so this is for all x fixed. Right, so now so now we want to use, so now since f prime at say z divided by g prime at z, since this fraction here as z goes to a, this is assumed to go to L, right? So this means that given epsilon greater than 0, there exists a delta greater than 0, so that if z here is less than a plus delta, right, then this fraction here, then f prime of z minus g prime of z is minus L is less than epsilon, right? So now coming back here, if you were starting with, so this here again was for all fixed x, right? You had this statement, right? And again, x0 was between y and x, right? So now if this x here, if x is delta close to the left endpoint of the interval, right? Then you would have that x0, right? But x0, remember that x0 is lying here, right? So since x0 would lie here, this means that also x0 here is right is in this interval here, right? And so this means that this number here you get is L with up to some, you know, it's L up to some error of like epsilon, right? So this here is almost equal to L. And so this means that this limit here, right, is almost equal to L within an error of epsilon, right? Okay, so this proves this version of the L'Hopital rule. And there's a second version, and that's in the notes, but I'll skip it actually for now, just because, you know, that was sort of from the last lecture, and it's very similar to this. Yeah? Sorry, why?
Why do we deduce that gx minus gy was not equal to 0?
Yeah, okay. So this is because g of x is supposed to be not equal to x for all x, right? And now I'm fixing x. Okay, so this here is non-zero. Then I'm letting y go to a, but then this here goes to 0 by assumption, right? So you see that if you're fixing x and you just take a y sufficiently close to a, then this denominator is definitely not 0, right? You really want to let this, you want to let y go to a, because then this here is eliminated, right? This is not part of the statement, the g of y, right? Okay. And so, again, as long as we started with an x that was sufficiently close to, right, if x was in this interval, then x0 is even further to the left, so this is also in this interval. We don't know exactly what x0 is, but it is in that interval, and so this means that this here is strictly smaller than epsilon. Okay, so another thing we talked about last time was this with the tail expansion. and that all of these things really came out of this Rothe theorem, and that was also the case for the tail expansion. So you have a function f. So this is just to remind you about the tail expansion. So you have a function f, and let's say that is defined on some interval here into R, and the function is, so f here is k times differentiable. So this means that f prime exists, f double prime up to the k derivative, right? So they all exist. And then the statement was, so then you looked at the k minus 1. This is the k minus 1 Taylor polynomial. And it was given by that k minus 1 of x is equal to, and now you're summing here from I equal to 0 to k minus 1, and you take the I derivative, this is the I derivative of f, and you do this in a, and you divide by a factorial, and then you're looking at x minus a to the power I. Right? So this was the k minus 1 Taylor polynomial. And then the Taylor expansion just told you that f here at some x was equal to p k minus 1, this Taylor polynomial, plus, and then this is what is usually referred to as a remainder term. And this was looked very similar to one of these terms. It was the k derivative of f, but then it was evaluated at a point c divided by k factorial times x minus a to the power k. And c here was supposed to lie between a and x. Okay. So that was this is the Taylor expansion theorem, right? And so the thing is that, so why is this so useful? And it is extremely useful in many different settings, also in much more general settings than what I'm describing here. And that is because that if you take a function here, then, and it may be a very complicated function, but this Taylor expansion theorem tells you that it is close to, if you want to evaluate it at some x, you can evaluate the Taylor polynomial. That's after all just a polynomial, so that's easy to evaluate. And then you get within this remainder term of the right answer. Okay, so that's how it always is used. And so the question is now, the natural question is, how well does the Taylor polynomial approximate the value of the given function? Right, so how well does the Taylor polynomial approximate the function? Okay, and of course to understand that, you need to estimate the remainder term. Let me write the remainder term here. So the remainder term, right, so the remainder term is, so I write this here as, so it really depends on x also, right? But I would just write it like this in here. So by this I mean the k derivative of f in c divided by k factorial, and then x minus a to the power k. So again, it depends on really also on it. Of course, it depends on a, but it also depends on x, right? And it's this thing here. The catch here is that you don't really know what c is, right? The only thing you know about c is that c is lying between a and x. So this is essentially all you need, all you know. About c. Okay. So now let's look at some examples. Let's look at two examples. So the first one is like a promising example, and the second one is much less promising. So the thing is that how well it approximates really depends on the function. Okay. But the first one is quite typical, though, example. So suppose that the function f of x is the exponential function. And then we have that the derivative is just the exponential function itself. So this means that if you take the derivative k times, then you just get the function itself. So this means that the k minus 1, this means that the k minus 1 Taylor polynomial, right? This is just the value of the function. I'll just write it out here. So this is the value, and now I do it for a equal to 0. And I'm assuming that b here, so I will think about this function here, f of x, this function, the exponential function, I'm going to think about it on the interval, say from minus 1 to 1. Into r. Maybe I'll just take it from 0 to 1 into r. Okay, so the Taylor polynomial, so I'm going to, so the Taylor polynomial, one also talk about that this, the Taylor polynomial is expanded around a, okay? So we talk about that the Taylor polynomial, so we talk about Taylor expansion around a, okay? And this just refer to that when you plug in a here, well then of course you have exact equality, right? And that all of the derivatives are evaluated at a, okay? So it's really like the Taylor polynomial, it's only a good approximation near a, right? So I want now to Taylor expand near the 0. And so the value here of the function is 1 at 0. The derivative is, right, so the derivative is also 1 because it's just this function itself. And so this is, so you get x, and then you get the next element in the tail expansion is x squared over 2 plus x squared over 3 factorial, and then x to the 4th over 4 factorial, etc., up to x to the power k minus 1 over k minus 1 factorial. Right? So this is the Taylor expansion, or take k minus 1 Taylor polynomial around 0. Okay. And so now, if you are interested in evaluating P, you want to say how well does this here approximate the original function, the exponential function. So you want to bound this thing here, right? So you want to have a bound for that. Well, the thing again is that f of x, you know that f of x is equal to this Taylor polynomial, and then plus this remainder term, right, in the C, right? Now C again has to lie, C will lie between a and x, and in this case a is 0. So it means that C here, so this means that here, C here is between 0 and x, right? And the remainder term here, this here was equal to that you took the k derivative of the function. So in this case, the k derivative of the function is the function itself. So this here is the value of the k derivative, and this is at C. This is the k derivative of the original function. And then you have to divide by a k factorial, and then it's x to the power k, like that, right? And so you see that if x here is now between 0 and 1, this means that this thing here, this remainder term here, the absolute value is, so C here is less than 1. So this means that this thing here is less than E. So it's less or equal to E divided by K factorial. This here is bounded by, since X is bounded by 1, this is bounded by 1. So you're getting this inequality here, right? And so you see that if K is very large, this is a tiny number, right? So it's a really good approximation. I mean, you don't even need to make K very large because it's exponential, right? Not exponential, it's factorial, yeah, right? Okay, so that's a kind of encouraging example. Let's say that the Taylor expansion is a very, in this case, is a very good approximation to the function. Another example that is less encouraging, and so again, the moral is that how well the Taylor expansion approximate the function depend on the function. So suppose that the function here was the function that was 0 here when x is less than 0, less or equal to 0, and when x is bigger than 0, then it is e to the minus 1 over x squared. Okay? So you see that when x becomes very, very small, you are looking at 1 over the squared. So this here is huge, right? But now it's with a minus sign. So this means that this thing here is incredibly small, right? And so it's clear that this function here is continuous at 0. It's clearly continuous everywhere else. But actually it's, sort of using in this sort of argument, it's easy to see that this function f here is infinite differentiable. So you can differentiate it infinite many times, and even at 0. Okay. And of course the derivative is right. So it's an example of a function that looks like this: is dead 0 until 0, and then it goes up like this. Right. And so the derivative at 0 is 0. Any derivative, however many times you take the derivative of this function. Sorry, this thing here. If you take any derivative and you evaluate at 0, you always get 0. Right? So this means that if you're looking at the Taylor expansion, at 0, so you're looking at this k-1 Taylor polynomial. This polynomial is all of the coefficient in the polynomial are 0, right? So this polynomial is just 0. So this means that if you're looking at f of x, well, f of x is actually equal to this remainder term, right? So it's somehow, you know, the Taylor polynomial is like too trivial. It doesn't really help you all that much, right? So it's equal to this remainder term. Okay. Yep.
Is there a way of